Okay, so linear combinations. When we talk about linear combinations, this is a basic linear combination that we know of. So 2x plus 3y minus 4 equals 0 represents a linear equation. Okay? So this is a linear combination of the variables x and y. This one, however, is nonlinear. 3x squared minus y plus 7 equal to 0. Well, that is a parabola. So if we rearrange that and got y equals 3x squared plus 7, we'd have a parabola. This is not a linear combination of the variables x and y. It does not create something linear. Okay. 4x minus 1 over y plus 10 is also nonlinear. Okay. If we tried to figure this out, or rearrange this, say it equals 0, into a function, we would have a rational function. And rational functions, as we know, are not linear. So this is not a linear combination of x and y as well. And this is also an example of a nonlinear combination of x and y. So when we want linear, we want the powers of x and y to be 1. Okay? So there is no power 2 or power 1/2 as you'd have in a square root, or a negative power as you'd have in 1 over y. Okay? It's a linear combination of those variables. Okay. In terms of vectors, if you got vectors u and v, then 3u plus 7v is a linear combination of the vectors u and v. You add those two vectors together and you get a resultant vector, okay, another vector. Okay. The vector 3, 7 can be written as 3i plus 7j. Okay. So the vector 3, 7 is a linear combination of vectors I and j. So it can be written as a linear combination of vectors I and j. What about if we have vectors u and v? Okay. Let's work out what 3u minus 2v is. So 3u minus 2v. Well, it's going to be 3 times 1 comma 4 minus 2 times negative 2 comma 3, and we get 3 comma 12 minus negative 4 comma 6, and 3 minus a negative 12 or negative 4, so 3 plus 4 is 7, and 12 minus 6 is 6. Okay. So we have the vector 7, 6 can be written as a linear combination of vectors u and v. Okay. Okay, so that vector can be written as a linear combination of u and v. So can 5, 8, the vector 5, 8, be written as a linear combination of u and v, the same vectors we looked at last time. Well, let's write it out here. So solution 5, 8 would have to equal some scalar multiple of u. So let's say that's a u plus a scalar multiple of v, b, v. Okay. We're now going to fill in what u and v are. So a times 1, 4, plus b times -2, 3. Multiply in the a and the b, and you get a 4a plus -2b and 3b, and that equals vector 5, 8. So the coordinate, the x coordinate 5 needs to equal a minus 2b. Okay. And the y coordinate 8 needs to equal 4a plus 3b. So the x coordinate and the y coordinate. Now what we have is a system of equations here. We have two linear combinations of a and b. Okay. And this is like finding the intersection point of two lines. So if I call this equation 1 and this equation 2, I want to eliminate a or b. I'm going to try and eliminate a first because it seems to be the easiest thing. If I multiply equation 1 by 4, I will be able to eliminate the a's. Okay, so I'm going to do that over here. So I'm going to do 4 times equation 1, which is going to be 4a minus 8b equals 20, and then equation 2 is going to be 4a plus 3b equals 8. Okay. Subtract. So I'm going to subtract the two. 4a minus 4a is 0a. Negative 8a minus 3b is going to be negative 11b. And 20 minus 8 is going to be 12. Okay. So there exists a b which is going to be negative 12 over 11. It's an ugly value, isn't it? Okay, I'm going to take that and I'm going to sub it into number 1. Okay, so number 1 would be then a equals 5 plus 2b, which equals 5 plus 2 times, well, b is negative 12 over 11. Okay, and that equals 5 plus negative 24 over 11. And I'm going to have to change 5 to something over 11, so that's going to be 55 over 11 minus 24 over 11, which gives us 31, right? 31 over 11. So there's a. Now that's pretty ugly. But now we can write it. So 5, comma 8 equals 31 over 11 times vector u minus 12 over 11 times vector v. So 5, 8 can be written as a linear combination of u and v.